Okay, so I just gave back some homeworks. And for Thursday, the assignment you're going to have is a programming assignment. So we'll do a little demo, maybe even 2 demos if we're lucky. Figure 7.24 is a schematic diagram of the translation process with a compiler. Now, this is going to require a bit of explanation, so listen up. I don't want you to get the wrong impression here, because what we're going to do with your translation project is not quite what happens when we translate from level HOL 6. And I want to make sure that everybody understands what a compiler does. So let's take a look at this figure 7.24 and see what it says. Now, figure 7.24 is applicable for a compiler. And what level does a compiler translate from? 6. HOL 6. Okay, so translates from HOL 6. Now, and so we can see on this figure what the compiler does. Now, what does any program do? Takes input, processes it, produces output. So the input to the compiler, to a C++ compiler, is a source program. Yeah, is a C++ program, a source program, which is a sequence of terminal characters, right? It's a string of terminal characters. And let's suppose that it translates to assembly language. So the output is a sequence of characters written in assembly language for whatever machine that the program is eventually going to execute on, right? Now, there are actually 2 parts to the compiler. Well, there's 2 parts to every compiler. Okay, one part of the compiler is what's called the syntax analysis. And the second part is called the semantics. Okay, so now, what does syntax mean?
Like structure?
Yeah, structure of what?
Of characters.
Yeah, of a sentence. Yeah, like a sentence, a valid string in the language. So it's the structure of it. So what a compiler does is it does these 2 things in order. First, it determines the syntax of the program. In other words, it analyzes it and figures out and does a parse.
Make sure it's valid.
To make sure it's valid, right. It has to make sure it's valid before it can do anything else. Okay, then after it determines if it's not valid, it stops and it doesn't do anything with the semantics. Okay, but if it is valid, then what it does is it has to actually generate the code. So generating the code is semantics. Semantics is the meaning. And the meaning of a program is what it does when it executes. Are you with me? Okay, so now here's the thing, you guys. We looked at some of the rules of production of the C++ programming language, right? Do you remember those slides that started? What was the start symbol? Translation unit, and then it could parse all that stuff. Okay, now I don't know if you remember this, but well, actually, let's back up to it here. Here, in this figure, 7.8, notice here that one of these rules of production is identifier, and then it says produces a letter, or an identifier followed by a letter, or an identifier followed by a digit, and then the letter produces A, B, C, D. Yeah? Mm-hmm. See? And so eventually this whole thing all goes back to but then those are used by these other ones, you know, and et cetera. So what this grammar looks like, this grammar is a little bit misleading, because it seems to, because what it's doing is it's the grammar for the entire C++ language, but it's all the way down, all the way from translation unit clear down to an individual letter, like the letter R. You see what I mean? Mm-hmm. Now, that's a little misleading, because even though that is even though this is the grammar of a subset of the C++ language, the syntax analysis does not use this grammar this way. Instead, what it does is it breaks it into two parts. And it determines the identifiers. What is digit? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? But let's go back, and what uses digit? Is there you see this integer constant? What is an integer constant? It's either a what? A digit, or a what? An integer constant followed by a digit. Mm-hmm. See? Mm-hmm. Okay, and then but wait, where do we get the plus and the minus? How can we get the, oh, maybe I didn't include that in this subset. I probably didn't include that in this. Oh, you're right, it is. Oh, well, that's an additive expression, right. Yeah, pluses and minuses and stuff. Okay, so, but the point is that a compiler, a C++ compiler, does not use this grammar all the way from translation unit, clear all the way down to an individual digit or an individual letter. Instead, it breaks it up into two parts, because and what it does, the way it works is it separately determines the tokens. Now, what is a token?
A group of characters.
It's a string of characters that have what?
Meaning as a group.
That have meaning as a group. All right? So now, the thing that I'm trying to get across here is that in this figure here, it shows the syntax broken into two parts. So the first part is called the Lexical Analyzer, and the second part is called the parser. Now, what the Lexical Analyzer does is, the lexical analysis, another word for the Lexical Analyzer is a tokenizer. So what it does is it goes through the sequence of terminals, and it groups, it detects the identifiers, it detects the integer constants, it detects, you see what I mean? It detects the reserved word. You see what I mean? It detects these what they're called tokens. It detects the tokens in a separate phase. It does that first. So what's the output of the lexical what is the input to the Lexical Analyzer?
The source program.
It's the source program, it's the sequence. But then what's the output of the Lexical Analyzer? It's no longer now a sequence of terminal characters. What is it?
It's a sequence of tokens.
It's a sequence of tokens. And what are those? Those are non-terminals.
Yeah.
Do you see what I mean? And one of the non-terminals in the C++ program would be identifier.
Right.
Are you with me? Mm-hmm. And then, okay, so it separates out those rules at the bottom of the tree. It separates them out, and it lets the Lexical Analyzer sort those out. And then the parser takes those and uses the C++ grammar to
Get down to
to get to translation unit, to parse it up to a translation unit. Is this clear?
An entire program goes from one translation unit, right?
Yeah, it does. It does, but it does it in. But the point of it is that grammar is not used by itself from top to bottom. Mm-hmm. Instead, for efficiency reasons, what compiler writers do, compiler designers do, what compiler writers do, the people who write the compilers, what they do is they break it up into two parts. And they do this pre-processing with the Lexical Analyzer to get the tokens. And then they use the grammar to do the, now, to do the complete parse from the translation unit all the way down.
Are compilers written in assembly language or machine?
Oh, no, they're not written in assembly language anymore. They're
had
not
to be at
written
one
in.
point, right?
And they did at one point.
So
That's the
now
boot
they use compilers
to write the compilers. Yeah, yeah. See, yeah, the Pioneer. Yeah, yeah. That's a really interesting question because now that we have high-level languages, we can use a high-level language to write a compiler in another high-level.
Okay.
So, but in the beginning, that's a boot process. It's and so the very first ones. So typically, what they would do is they would write a limited one with limited features in the low-level language. And then once they had that limited one, then they could write the compiler in that language, and then the compiler could compile itself. Yeah, it's really a very thought-provoking process. Okay, so now, to get back to this figure 7.24. So I'm here to tell you that if you're going to write a C++ compiler, the way you would do it, the way it's always done is the lexical analyzer determines the tokens, and furthermore, the lexical analyzer is based on a finite state machine. That's the other thing. It's based on a finite state machine. Okay? And we've seen examples of finite state machines that recognize identifiers and that recognize numbers, yeah? Signed integers, And we see how to construct it on paper, how to construct a finite state machine on paper. And now it's beyond the scope of this course to show you how to implement a grammar in a program. I kind of long for the day. We used to actually have a compiler construction course, and students would and we had this great. It was a,
Is there a project like?
And there was a project to actually translate a language and to get the machine code out, and there are lots of techniques. There's top-down parsing and bottom-up parsing, and there's lots of really interesting theory. And what we used that before we had the automata theory course. That's where students got their automata theory, but it was a practical one. But now things got shuffled around, and we don't do that anymore. Now we had the automata theory course for all that stuff. But anyway, I kind of hated to see that go, but too many other things. There was no object-oriented programming in those days. Now we got to do object-oriented programming. And, so anyway, things change. The field changes. Okay, so does everybody understand? The point is that for the syntax part, in a compiler, the lexical analysis is done with finite state machines, and the parsing is done with a grammar. Now, here's the thing, you guys, for your project. Your project is not a compiler. Instead, your project is what?
Assembler.
It's an assembler. So let's look here. But assembler translates from what?
5 to 3.
Translates from ASMB 5. So an assembly language is not nearly as complicated as a high-order language.
We only have like 32 instructions.
Yeah, and furthermore, those instructions are all line-oriented.
Mm-hmm.
There's no nesting.
Right.
You see what I mean? Because what can you do in C++? You can have an if inside of an if inside of a while.
Yeah.
Yeah? But you can't do that in assembly language. Okay? So assembly languages are much simpler. In fact, they are so simple that guess what we can do?
Build one.
Not only build one, but guess how we can do the parser. Instead of using the grammar for a parser, what are we going to use?
Assembly language.
No.
Finite state machine.
We're going to use a finite state machine, is right. Are you with me? But I don't want you to get the wrong idea.
Oh, okay.
I don't want you to get the wrong idea. Our project, we're going to have a finite state machine for the lexical analyzer, and we're going to have another finite state machine at a higher level of abstraction for the parser.
Okay.
Do you see what I'm saying?
Normally you wouldn't.
But well, for a compiler, I want you to understand that for a compiler, it would be a grammar for the high level one.
Okay. But because this is so simple.
Because this is simple, and assembly language is simple, we can do it with just finite state machines. With a finite state machine at the syntax level
Could it be
part.
done for a compiler, or it would just be a really, really nasty?
It could be, and it wouldn't be that nasty, but we just don't have time.
Oh, okay.
You know, we would have to learn some, you know, we'd have to learn compiler techniques, and it wouldn't be necessary. You know what I mean? It's not necessary, so
Okay.
anyway. But it's really a compiler construction and parsing a high-level language is really a very fascinating topic, but the thing of it is that a lot of research has been done on that, and most of the research that's been done on the parsing aspect is pretty much people have figured out pretty much all the theoretical ramifications of that. The hard part is the code generation. Okay, and that's where lots of people, all the work now on compilers is all on how to do the best job at code generation. That's much more difficult. The parsing part is pretty much closed. I mean, that's pretty much solved. Computer scientists have solved that problem. And so most of the effort is on the code generation part. But the main thing is, just remember, even though this is for a compiler, and with the compiler, the parser, the parser is based on a grammar, but for our assembler, the parser is going to be based on a finite state machine. So now what we want to do is, this is going to be fun. Now we're getting to the point where, how do you program these things? Because here's what your project is going to do. Your project is going to, in your project, you're going to write a finite state machine for the Lexical Analyzer. Are you with me? And then after you write that, you're going to write a what? Another finite state machine for the parser at a higher level of abstraction. So the output of the first finite state machine is going to be, the input to the Lexical Analyzer is going to be a string of characters from the terminal alphabet. The output will be a stream of tokens. And then for the parser generation, the input will be a stream of tokens, and the output will be, yes, it's correct, or no, it's not. And if it is correct, then it will generate code. So it's really important that everybody understands the overall structure of the project at this point.
Our code generator is going to be very, very defined. Is it?
The code that you're going to
the code. This instruction keyword.
Yes,
these numbers.
Yes, it's going to be like 50007A.
Right.
That's what it's going to be.
If we get character out.
If you get, yeah. That's what it's going to be. That's what the code generation is going to be. And I think it's really cool for you to be working on code generation. Because once we get you started on your project, we'll go back to chapter 6, and we will actually see what the compiler does in going from C++ to assembler. And as we're doing that, it's really interesting to think, now geez, how does the compiler do, how is it going to go from here to here? And because you'll be working on another translator, and it all comes together very nicely, I think. Okay, so next item is, there are two coding techniques to implement a finite state machine. The first one is called table lookup, and the second one is called direct code. And what we're going to do is, your homework assignment for Thursday is to modify a table lookup program that we're going to look at here. Okay? And then here's what we're going to do. We're going to illustrate this with this particular finite state machine. Do you remember this machine? We come in, oops. We come in here with state A, and what we're going to do is, if we have a letter, we're going to go to what? State B, which is the final state. And then if we're in state B and we either get a what? A letter or a digit, we'll stay in state B, which is the final state. But if we get a digit, we'll go to state C. And then if we get a letter or a digit, we'll stay in state C. And then when we end and we're not in the final state, then it's not a valid what? What is this thing?
String?
What kind?
Oh, identifier.
It's an identifier. What's the rule for an identifier?
Has to start with a letter.
Has to start with a letter. Are you with me? Do you remember this? Do you remember this finite state machine? These are the very first ones we did. Yeah?
Yeah.
Now what is this? This is the state what?
Transition diagram?
State transition diagram. The technique we're going to use is the table lookup technique. So what is our implementation going to be based on? Not the state transition diagram, but the what?
State transition table.
The state transition table, which you remember looks like this. Now, do you remember, you see how this matches this? Okay, and now what we're going to do is here. What we're going to do is, with the table lookup technique, we actually put this table in your program.
Two-dimensional array?
Two-dimensional array. That's the idea. The state transition table is a two-dimensional array in your program. That's the table lookup technique. So, without further ado, we will do a demo. Okay. Okay, so here's our demo, and we're going to demo figure 7.25. So we'll right-click on this and set this as the main project. You notice that this is we're running NetBeans here, right? So we're running NetBeans, and here's figure 725. And here, if you look in figure 725 in the project, these are the source packages, and our program is in the what's called the default package section. And then here is figure 0725 main.java. Now the code for this, well here, let's go ahead and double click it. So here's the code for it, but I think we'll inspect this code from the slides. Okay, so we'll look at that in a minute. What I want to do now is just demo the application. So let's run the main project. Now watch what happens. And we see a little window here. And what does it say on the title bar of the window? Figure 7.25. And here's a label that says enter a string of letters and digits. And here's a button that says parse. So let's enter ABC3. And that, down here is the output pane, right? So if I click parse, let's see what happens. ABC3 is a valid identifier. Yay! Isn't that exciting? And it doesn't matter if it's, you know, AB 80s da 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 da. What is this?
Valid identifier.
ABC blah, 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 is a valid identifier, right? On the other hand, if I put a 2 here, what's going to happen? 2 da 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 is not a valid identifier, right? So if it starts with a now actually that's an interesting question what you asked, because if we said ABC and we know that ABC here is a valid identifier, and what did you say to put?
Like a symbol.
Put like a something that's not, there's a deficiency in this program.
Not valid transition. Okay.
Oh wait, it does say that it's not a valid identifier.
What if you put it at the end?
Oh, I think maybe that's the problem. Yeah, I think, well, I'm not sure. Hold on. There's a deficiency here somewhere. Oh, yeah, big deficiency. So your problem is your exercise is to correct this deficiency.
Oh, really?
Yeah. And I think also if you put it in the middle, you know, like this is it's still going to say it's a valid ID, even though it isn't, because it has this extraneous here. You'll see from the code why this works this way. All right. So anyway, so now let's stop the demo and take a look at the code. Okay, so that's the demo, and here's a little screenshot of what we just did. CAB3 is a valid identifier, 3CAB is not a valid identifier, and here's the code. So now, as we have done before, I've done all of the code for you for the graphical user interface in Java. If you're interested, you can go through that, but you can see right here there's a JFrame as the main window frame, JPanel is the input panel is the JPanel. There's a label, there's a text field. The text field is what we input, where we did the input. And then there's a button panel, and there's a button. And here is the code for all the setup stuff. You see how we put the figure 7.25 in there, so you can change that if you want to change the title. And there's some more. And then we lay out the label in the text field from top to bottom, so you see the label. Enter a string of letters and digits, so you can change that if you want to. And then, and where's the button? Bottom. So, and remember what was on the button? The word parse. So there's new J button, parse, so anyway, you can do all that stuff. And then add action listener. Do you remember why we have an add action listener for text field.add action listener and a button.add action listener? Do you remember why there's two of those? I should have demoed that actually. The second one is we add action listener to the button. So when you press the button, it would do its thing. But why do we have the one above it?
To show maybe the cursor.
No.
Was the cursor button disabled when we didn't have text?
No, it wasn't. It's you know how users like to put input a field and then press return, or press enter,
Yeah.
instead of pressing the button.
Oh.
That's what that does. Should have demoed that.
Okay.
Is that cool? Nice little user feature. Okay, and then we do all that other stuff, monkeying around, and then here's our public static void main. So that's the main program, and so what it does is all that stuff that we've done before, and then create and show GUI. The run method happens whenever you start the program, yeah, and that creates and shows. That does the create and show GUI. Okay, so now here's the code that you're going to be responsible for, or that the kind of yeah. So in this main program, first of all we have a public static boolean is alpha char. Now, and do you see how it works? Do you see the logic there on how that works? It just checks to see if the ch is the parameter. Yeah, which is a char, and we just check. If a is lowercase a is less than or equal to ch, and ch is less than or equal to z, or a is it, yeah. And so that returns either what is it? What does it return? Boolean. Yeah, so true or false, right? And now you guys check this out. What states did we have here? Let's look over here. What did we call the states? A, B, and C. Yeah? So how do we encode, how do we represent A, B, and C? They are what? They are integers. In fact, they are integer constants. What does static mean?
One
per class instead of one per object. And what does final mean?
The constant part?
Yeah, that's what makes it a constant. You can't change it. That's its final value. It can't change. It can't ever change. All right. So everybody see that that's like constant
Okay.
in C++. Okay. And we call it SA for state A, SB for state B, and SC for state C. And they are just integer values 0, 1, and 2. So we just put those there to make them. We name the states because they're the names of these states here. Okay. That's just for documentation. Self-documentation. And now you guys, how many characters do we have in the alphabet?
2.
2. And so what are those?
0 and 1.
Yeah, a T letter and a T digit. Are you with me? So we don't have a T
Plus.
something else. Yeah. Which is probably what we need. Huh? Okay, and now check this out, you guys. Here is the state transition table. Static final int bracket bracket. So what does that make it?
Two-dimensional.
A two-dimensional array. And furthermore, let's go back here. Let's go back here to our state transition table. Look on figure 7.11. What is the state transition table? Given a current state A and that our next state is a letter, what does it give us?
A new state.
the new, yeah, what the next state is. So do you, and what is the body of this table? B, C, B, B, C, C, right? Well, look.
BC, BB.
BC, BB, CC. All right? And furthermore, what is this? It's static final int, and then, so SB, yeah, well, that's it. I mean, I don't know what else I can say. That's 0, you know, and that's indexed. You know how in C and Java, arrays are indexed starting at 0? So it's 0, 1, 2. So do you see how that corresponds? You see how,
Oh, yeah.
you see how 0,
Yeah, that makes sense.
so now, yeah, so you see why we did 0, 1, we encoded 0, 1, 2 and 0, 1. 0, 1, 2 for the states and then 0, 1 for the digits. Is that clear? And notice that it's an array of arrays. So the brace initializes the array.
Oh, there it is.
You see what I mean? The brace, the initial brace initializes, is the outer brace, and then you have 3 arrays with 2 elements each inside the outer brace.
A loop.
Right, this just initializes. We haven't actually done the processing. This sets the table up. This is how the table is set up. Is everybody clear on how that works? Now the question is, what happens when you press the button? Now watch this. So here's what happens when you press the button. When you press the button, what happens is action performed. Okay, this defines what happens when you press the, or if the cursor is in the thing, you press enter. Okay. So this is the action performed. So what action gets performed? Okay, now first of all, here, what is line? It says string line. So what is that capital S string? That's a Java string type. Are you with me? So so line is like this. Now whenever the user put ABC3 in there, then what that did is that gave line the value A, B, C, 3. You see what I mean? That's what it gave it. And furthermore, what is A? What was this character A? This character A is,
CH gets lined up.
yeah, it's line dot char at 0. This A is line dot char at 0.
Where's that at? Or just
Okay, so look, okay.
I get why it would be that. I just didn't see that on here.
Well, you have to understand, line is a Java string type. Are you with me? And char at is a method that's built into the Java, that's provided for the Java string type. And what you do is, whatever index you give it here, it's the character from the string at that position. So this is sub 0, sub 1, sub 2, sub 3. Is everybody clear? So look, what it does is char is type C, or CH is of type char. And furthermore, okay, so that's this character. But now the character that we use to make the transitions is, we're going to call that an FSM char. And that's an int. Are you with me? And so what happens? For int I get 0, I less than line dot length, I plus plus. So what does that do? Boom, 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 boom. That loops through this whole thing, right? So 0, 1, 2, 3. Yeah? And then the first, so CH gets line dot char at. So the first time it goes through the loop, CH gets what? The letter A. Yeah, and then what? Now look. FSM char gets what? That's the trinary operator. So is alpha CH? Remember we wrote that one? So here, would that be true or false?
Sure.
That would be true. So FSM char would get what? T letter. Oh wait, we skipped a very crucial thing. What state do we start off in? Yeah. There's a that was the most important one of all. This is called the state. Yeah, this is called the state variable. Are you with me? Yeah. It's state variable. And the state variable, so we have a variable named state, which is the state variable, which keeps track of what? The state we are in. And what is that initialization?
Start state.
Yeah, S.SA. So the state starts off, that assignment statement does SA, state A. That's the initial state. And then look, you guys, what it does. After it does FSM char gets, the is alpha, what does it do?
State gets FSM sub state.
Sub
So does that give
Oh.
the,
FSM char.
so the first one's the row and the second one's the column? Is that right?
Let's go back
But when you call it there.
here.
Yeah.
Here.
Because then it
So
would
we're-
go to.
We pass
only on
state
the
through
first
so we
line.
know which one we're in, and then we find out if it's a letter or a digit to go with.
It's a letter, yeah. We find out if it's a letter or a digit because the transition is either on a letter or it's on a digit. Are you with me? And so it looks up on this table. This, in fact, that line right there, state gets FSM sub state sub FSM char, that is the table lookup.
Yeah.
It's looking up in the table, given what the current character is. Are you with me? Given what the current character is, and what the current state is. Are you with me? Notice what it puts. It does the C. What does it give it in the subscript? It gives it state, which is the current state. Are you with me? And what? FSM char, which is the current character. And then it does the and then what is that? And then what? It looks at it, and then what happens? State changes. So here, boom. It's no longer SA. Now it's what? SB, because that was a letter.
Okay. And then we just say if.
And you just loop through until you get to the end. And at the end, what do you check?
If it's a file state.
Yeah. And so how do we check it? System.printf. Oh, by the way, notice how this printf works. Do you see the sentence that gets printed out is %s is a valid identifier, period, --n, end quote, and then line. But now what is the value of line? Line is this what? ABC3. Are you with me? So the placeholder for a string is %s. So do you remember what it said when we demoed it? It said ABC3 is a valid identifier. So does everybody see how that printf works? Printf is just so flexible. I used to use the other print ones, but as soon as they had printf, it's just so flexible. I think it's really good for you to use printf all the time. And this is an example of how to use it to print out a string. I think, have we done this before? I mean, we've done printf before, I think.
Is it always %s though?
No, it's %s. S is for string. If you want to print out an integer, I think it's %d. Was it d? I keep forgetting.
We might use D.
Yeah. And so it's different depending on what the thing that you're printing out. And you can have more than one thing there. Like you could have two strings. You could say %s is a valid %s again, and then you could have a string, a first string and a second string, and then the first string would go in the first one, and the second string would go in the second one.
So it's like the QT with the dot.
Yeah, it's very common formatting. It's like the Qt, like what we did with in C++ with the Qt stuff. Okay, and then else it's not a valid identifier. So now your problem, should you decide to accept it, Mr. Phelps, is to correct that problem, that shortcome that we had. And I think what you'll need is, instead of having a
Well, it thinks that anything
it thinks
that's not a letter is.
Yeah, that's what it does. That's what it thinks. So what you'll need is a transition on something else.
Invalid transition.
Yeah, or whatever. Yeah. An other, you'll need,
Letter.
letter digit other, whatever. Okay, and then program it accordingly so that it works. All right, is everybody good with that? Okay, so now what we're going to do is we're going to take a look. Actually, I think what I'll do is, just so that we can just so that I can show you, I think we can squeeze in another demo, and then we won't have to demo next time. All right, so figure 7.19b. So now what the program that's going to be due after Thursday, which by the way we have a spring break, right? So you'll have lots of time to think about this one. The finite state machine that we're going to implement with this next example is it's going to do quite a bit actually. It's a finite state machine to parse a possibly signed integer. Now, does this figure look familiar, 7.19b? Okay, but now this time we are not going to use the table lookup technique. This time we are going to use what is known as the direct code technique. And I'll tell you right now that this is the technique that you're going to use for your project. We're not going to use the table lookup technique, although it's important for you to know how it works because most automated lexical analyzers do table lookup. But it turns out to be very easy. It turns out to be a little bit easier to generate your code. It's a little bit more easy. Well, there's advantages and disadvantages to each approach. And with the direct code technique, it's a little bit easier to do the actual code generation. You'll see why when you get into your project. Okay? So now, do you remember how this worked? If there's a digit, then right. It goes to the M state, and then if there's more digits, it stays in the M state. But if it starts with a plus or a hyphen, then it goes to the F state, and then after that, if there's a digit, it goes to the M state. And then, yeah. But now here's another thing. We're going to do more than just syntax now. Another thing we're going to do with this project is, with this example, is we're not only going to parse the integer value, we are actually going to convert it from a string to an int. And it turns out that that's going to be part of our code generation processing that we're going to do eventually. Okay? So I think what we'll do is, I think we'll have time just to, I'll give the demo of this one. It's not too exciting, but anyway, here it is. Okay, so here's our other demo. So we're going to close figure 725, and we will take a look at figure 726. We'll right-click on this and set this as the main project. And now, you guys, here's one thing that we need to be aware of, and that is, in this project, which is more similar to what your project is going to be, there's not just one main program. Look, check this out, sports fans. What we have is, not only do we have figure 0726 main.java, we also have parser.java and state.java. Okay, so we're going to have separate files for each one of these classes. We're going to have more than one class in this project. So just to demo what the program does, check it out. It says enter a number. Okay, suppose I enter a number. I say J43, and I do parse this. What do you suppose is going to happen? Oh, invalid entry. Okay, well, okay, instead of J43, suppose I just say 43. Now what's it going to say? Parse. Oh, number equals 43. And furthermore, if I put a plus here and I do parse, it will say what? Number equals 43. But if I say minus and I do parse, it will say number equals minus 43. And furthermore, if I try to get fancy and put like a plus in the middle, it will say what? Invalid entry. Okay? So that's basically what this program does. But what's interesting about it is it not only determines whether this is a valid number or not, but if it is a valid number, like if it's 436, it actually converts that string of characters from a string of characters to an int. that has the value 436. It's kind of hard to tell from this output that it does that. In fact, it's impossible to tell. But that's what it does. We'll see from the code that that's what it does. Okay, so that's the demo. Okay, so that's the demo, and I won't bother to do this demo again on Thursday because you've seen it now, and we'll take a look at the code on Thursday. All right? Is everybody happy? Okay, see you next time.